Okay, so for this next problem we've been asked to find the x and y components of a couple of forces. So we've got a 50 Newton force, we've got a 60 kilonewton force acting in different directions, and we're going to find the x and y components. Now before I do those, I just quickly wanted to point out some differences between the problems involving displacement vectors and problems involving force vectors. Now the method you use is exactly the same, but it does result in some differences in how we draw these problems. So first of all, let's think about the little robot we had, for example, and suppose it moves a certain distance in the x direction, so that's your x component, and then it moves a certain distance in the y direction, that's your y component or your y displacement vector. And to find the resultant, all you do is you join the start of the first vector with the end of the last vector. You get your result. So it's basically a shortcut from your starting position to your finishing position. Now what's special about displacement vectors is that they actually represent movement. So this little robot started at this point, moved along this displacement vector and got to the end. Then it moved along the second displacement vector, so the y component, and ended up here. And the resultant vector was just the vector that joins the starting point to the finishing point. So you take your vectors, put them nose to tail, join them start to end, and you get your resultant. Now we can use exactly the same method to join forces, but we just have to be careful how we draw them so we don't confuse people. So one of the differences for forces is that if, suppose we've got a bit of a hook that's fixed into the ground, so that's what we've got here, and on that you'd have a couple of forces acting. So you've got a force acting, or an x component of force in this direction, and you've got a y component of force in the other direction. The first difference is that both of these components are acting simultaneously, so you're pulling in the x direction at the same time as you're pulling in the y direction, unlike the displacement vectors where you first had a displacement in the x direction, then you moved in the y direction. The second difference is that there's no movement involved in these vectors, so it's not as if this little hook is moving along this vector and getting to here. The hook is always staying in the same place. All that vector represents is the direction you're pulling and how hard you're pulling that little hook. And so if you were to pull that hook gently, you'd end up with a very small vector. If you apply a lot of force and you pull with all your might, you end up with a much larger vector. But to find the resultant vector, we can use the same method. So we can take this vector, we can place it nose to tail, and your resultant vector is the vector that joins those two vectors together. So your resultant vector is like so. Alternatively, just get rid of those. You didn't need to move the y vector. You could have moved the x vector and placed it nose to tail. So you could have taken this vector, place it nose to tail with the first vector, then draw your resultant, then draw your resultant, and you would have got exactly the same answer. Now the problem with this is it looks like this force, so the x component, is now acting on a different point. It looks like it's pulling the green cross here. It's looking like it's pulling at that point. So when we draw these, we don't want to draw the vectors in a different position. We want to keep them where they are, and we can just imagine placing them nose to tail. So you could imagine the y component would end up over here. Or the x component, you could have moved that nose to tail, and you would have moved it up to here. And then you would have drawn your resultant vector. Like so. And this is how we're going to draw it. So basically you end up drawing a rectangular box, so a rectangle from the end of each of the vectors, and the resultant is the diagonal of that box. But always you're remembering that the reason you can do that is because basically it's just the same as joining those two vectors. Oh, let me get that properly. Just the same as getting those two vectors nose to tail, so you're putting those nose to tail. But we don't want to draw it that way because it looks like the position of the force has moved, which it hasn't. So having covered that background, let's have a look at doing these two problems. So starting with A, we've got to find the x and y components of that 50 Newton force. So first thing to do is we'll just quickly draw our x and y axes. And I'm just going to draw those separately so they don't get in the way when I'm trying to mark on my opposite, adjacent and hypotenuse for SOHCAHTOA, or my A, B and C if I was using Pythagoras. And then we'll just try and draw that line to scale. So 34 degrees and 50 newtons long. So I'll just use 10 small divisions for 10 newtons. So just make the pen a bit thicker. 10, 20, 30, 40, 50. As we just talked about, if we're finding x and y components, when we put those nose to tail, they should combine to give the resultant vector. So when we're doing displacement vectors, we'd have drawn it like this, figured out how much you move in the x direction and y direction to get to the end point. But this time we're not talking about displacements, we're talking about forces. And so those two forces need to be acting on the same point. So we're going to, this y component is going to have the same start point, and we're just going to imagine drawing nose to tail, and in the end we'll end up making a rectangle where that resultant vector is the diagonal. I should have done that in red. Okay, so I'm running out of space a little bit, so I'm going to just move this across a fraction. So we know that this side is the same length. So in fact, this is f of x, and this is f of y, fy. But this will be the same length as fy, so this has got the same magnitude. So we can just use this triangle here to calculate everything we need. Now the other thing we've got that I haven't marked on yet is that this angle is 34 degrees. Okay, same procedure as usual, find your right angle. If you can't find a right angle, you can't use SOHCAHTOA or Pythagoras. Have a look, opposite the right angle is your hypotenuse, opposite the angle is opposite, adjacent to that angle is adjacent. Suppose we want to start by finding f of x first. And so we've got the hypotenuse, f of x is adjacent, so it's ka and it's cos. So cos of 34 degrees is equal to adjacent over hypotenuse. Cos of 34 degrees is equal to fx over 50 newtons times both sides by 50 newtons. That will give you f of x equals 50 cos 34. And then if you put that into your calculator, you'll find that f of x is going to be 41.5 newtons. Let's just check quickly to see if that looks about right. So we've got 10, 20, 30, 40. It looks about right. So what I'll do, just to show that I've checked that number so I don't go and check it again, I'll just give it one underline. Now we want to find f of y. So f of y is over here. And so we've got opposite. We'll probably use the hypotenuse again because that was the one we're given. We could have used the value we've just calculated, which I've forgotten to put units on. But better to use the numbers you've been given just in case you've made a mistake calculating this value. So this time sine of 34 degrees is equal to opposite over hypotenuse. Sine 34 degrees, opposite is f of y, hypotenuse is 50, times both sides by 50, swap them around, f of y is equal to 50 sine 34, which is equal to, if you put it in your calculator, 28.0 newtons. Check it makes sense. So this time we've got 10, 20, 28, looks about right. We'll underline it to show, sorry about that, we'll underline it to show that we've checked it. And then we'll just write out the answer. So x and y components are f of x is equal to 41.5 newtons, f of y is equal to 28.0 newtons. No bother. Okay, so let's look at the next one now. So we'll just move this down so we can see it while we're doing the working. So the reason we included this example is because this time the difference is that the force is heading in the negative direction compared to the x and y axis. You've got to look out for that. So your x is heading this way, your y is heading this way, but your force is heading in a negative direction. Now, I'll just do a very quick sketch. So you could have x and y like so. The force could be in any of the quadrants that are formed by the axes. And so if your resultant was heading in this direction, it would have a positive x and a positive y. In this direction, it's going to have positive x, but it's going to be a negative y. This direction, both negative. So y is heading this way, x is heading this way. For this direction, both your y component and your x component are negative. Last one, in this quadrant, so each of these sections is called a quadrant. So this is one quadrant, another quadrant, another quadrant, another quadrant. This time the y is in the positive direction, but the x is negative when this vector is heading this way. So when you're starting a problem, just have a look at it when you start off and make sure you're clear about which components are going to be positive and which components are going to be negative. So this is question B. Again, we'll just draw the axes first separately to keep them out of the way. So I've got y and x, they are heading that way. X this way, y that way. And again we'll draw, so one thing this ruler I can't draw 147 degrees clockwise. Once I get to here it goes to 90 and then it goes back again. But what I can do is I can think to myself, well, this angle plus this one, they're going to make a straight line. So they must add up to 180. So this angle here, 147, plus this angle is 180. So this angle here must be 33 degrees. That means I can draw it. And this time it's 60 kilonewtons. So again, if we were working on real calcs, we'd be thinking to ourselves like 60 kilonewtons and make it real. So that's divide by 10, it's about 6 tons of force. Okay, now we're going to draw this one. If I draw it the same scale as last time, it's going to get a bit big, so I'll just do 5 divisions is equal to 10 kilonewtons. So we're going to have 10, 20, 30, 40, 50, 60 kilonewtons, just approximately. And then we're going to use the same process to draw the x and y components. So I'm just imagining that rectangle. I'm going to have an x component in this direction, solid line, and I'm just imagining where that rectangle is going to end up for when to stop. So it should have ended a bit earlier, should have ended a bit here. And then we've got so that was the y component, now we've got the x component. This is f y, it's in the y direction, and this is fx. Just complete that rectangle. Yeah, good enough. And what angle do we know? We've already figured out over here that this angle inside is 33 degrees. In the right colour. That's going to be 33 degrees. We could have used 147 degrees, but you'd have to know a little bit more about how to work with sine, cos and tan for when the angles are bigger than 180 degrees. So we'll just stick with this method where we just figure out using straight lines or right angles, angles adding up to straight lines or angles, right angles to figure out an angle inside the triangle. Okay, again, we haven't moved head to tail, but we can imagine that this here is the same as f of y. We find our right angle, it's here. So opposite the right angle is the hypotenuse, opposite the angle's opposite, adjacent to the angle's adjacent. So f of x first. So we're trying to find f of x, adjacent over hypotenuse, using cos. So f of, cos of 33 degrees is equal to adjacent over hypotenuse. So cos of 33 degrees is equal to f of x divided by, I haven't written that on, 60 kilonewtons. Therefore, fx is equal to 60 cos 33 degrees. Put that in the calculator and you'll get 50.3 kilonewtons. Now just going back and checking, our x direction is this way, but our f of x is heading in the opposite direction. So all of this should have been negative, 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 negative. And so it should have been negative. Let's just roughly check the value. So we have 10, 20, 30, 40, almost 50. Yeah, it's a pretty rough diagram, so that looks about right. Let's underline it to show we've checked it. So again, what I did was I went back and had another look at my axes. I noticed that f of x is heading in the opposite direction from the x-axis. Therefore, the answer must be negative. So f of x is negative 50.3 kilonewtons. Now for f of y, so f of y is over here on that triangle. So it's opposite. We're again going to use the hypotenuse because that was what we're given. So it's so sine. So sine 33 degrees equals opposite over hypotenuse. Let's think about the negative first this time. So f of y is heading in this direction, or fy is heading in this direction, but the y-axis is the opposite direction, so this must also be negative. So therefore sine 33 degrees is equal to negative. Opposite is f of y over hypotenuse is 60 kilonewtons. Therefore f of y must be equal to negative 60 sine 33 degrees. Put it in the calculator and you're going to get minus 32.7 kilonewtons. Quick check, it's a bit small so it's not a terribly useful check. We've got 10, 20, 30, it's all drawn a little bit too big, it's a little bit bigger than that, so that looks okay. So let's underline that one to show we've checked it. Write the answer. So x and y components are f of x, fx, equals minus 50.3 kilonewtons, and fy equals minus 32.7 kilonewtons. Underline it to show so it's easy for you to find your answer later. You should have done the same with this one. So let's go back and do it now. That's the two questions finished, where we determined the x and y components from a force vector.